Hi! We all know that as we age, our skin starts getting stretchy and droopy in many places. But it is a proven scientific and medical fact that if you apply high enough voltage across your loose skin, you will die. Yes, I'll be talking about the skin effect. But the electrical skin effect has nothing to do with the live skin. All it's about is that when we run AC current through a conductor, the magnetic fields inside the conductor push the flow of current towards the surface or the skin of the conductor. Does it mean those fields push charges to the surface of the conductor to flow? If so, I can show it easily. Same as how my sponsor Brilliant easily shows simple to complex concepts through their interactive lessons. There is no regret in signing up through my link brilliant.org/electroboom. You get full 30 days free to try Brilliant and learn as much as you can. But most importantly, you actually learn to program, to science, to analyze data, and more at the end. To show how charges go to the surface, I have two wires running side by side, and I will run current in the same direction in both with my power supply. And we can see these wires separate apart as we turn on the supply, see? Oh sh! Middle fingers for B field. Well, yes. According to the right-hand rule, for same direction currents, the force on wires is towards each other. They repel each other when the currents run in opposites. I already knew it too. That's the whole reason for lightning. Say when charges start flowing from clouds to the ground, the magnetic fields pull them together and eventually create a single channel. Now, this confuses me for two reasons. First problem I have is we had a debate with Veritasium a while back where we agreed how spread of charges in a wire is uniform. And now this, suggesting magnetic fields should pull charges towards the center of the wire? And second problem is, well, in skin effect, the charges should flow at the outer skin layer of the conductor, not at the center. My test was DC though. It might be something AC does. I'm going to run AC current through my wires. I need to limit the current through the wires, of course. Using my auto transformer. Same direction AC current through the wires. Let's see. For the love of and the wires got attracted together and melted shut. And so we read Wikipedia. The magnetic fields generate eddy currents that oppose the flow in the middle. Oh. Hi, I'm an expert in skin effect now. Well, before explaining skin effect, let's talk about my experiments of attracting wires versus the flow of charges remaining uniform inside the wire rather than accumulating in the middle. According to Lorentz force law, there are two types of forces affecting moving charges: electric and magnetic forces. In a wire though, or especially in short distances, electric force is typically the dominant force between the two, significantly larger than the magnetic force. So in a wire, between magnetic fields pushing charges to the middle and charges wanting to return back to their positions to create electric equilibrium, of course electric force wins. Magnetic force is in no way strong enough to create such a charge imbalance in a wire, but it's there. So in my opinion, it might create an incredibly small charge imbalance inside the wire we can ignore. I'll park that thought for now. Let me know if there is an article on this in the comments. The reason the two wires jump at each other though is because, to simplify, ignoring the small effect of relativity of objects in motion, there is no charge imbalance or electric force because electrons and protons move together in the wire structure. There is only an attracting magnetic force, which is due to the relativity of objects in motion. Now, to skin effect, it's not about charges moving to the surface of a conductor. It's about the electric current not flowing in the middle. The charge distribution is still in equilibrium in the wire. This can only happen in AC though. The reason is that only alternating current creates changing magnetic fields that inside the wire induce eddy currents. I have explained eddy current back in my old video, you can watch for more details. But basically, when AC current flows one way in the wire in a snapshot of time, creating magnetic fields in a certain direction, the resulting eddy currents are always such that they amplify the surface currents but oppose the center currents. So less current in the middle. I think there's a way for me to show that the current is lower in the middle of the wire by making a wire with multiple strands. I have 7 short strands of wire and I'll place one of them in the center and the rest around it. Like this. I soldered all of them together on one side, but on the other side I separated the center one from the rest of the 6. See, according to the skin effect equation, the skin depth, which is a depth in the wire skin where over 60% of the current runs through, reduces as the frequency rises. Like in copper, it is 8.4 millimeters at 60 Hz, but 0.2 millimeters at 100 kilohertz. So I'm thinking with my arrangement of wires, the center wire current should stop as frequency rises. Now to measure the current, well, that was a waste of time experiment. I'm an idiot. Remember those eddy currents? I cut right through them by using multiple strands, killing them. This is one of the good ways to reduce skin effect. In my measurements, the center and outer currents remain close until frequency rises above 10 MHz, after which it enters the realm of black magic. How can I measure it then? Okay, here's my next scheme. To avoid cutting the eddy currents, I'm using a wide copper tape. Then inject AC current one way and pulling it out from the center and outer layers separately to measure. Another pointless effort. So as I measured, the middle current actually drops, but only when I get to 5 MHz, after which it is black magic again. Middle current should drop way more significantly at much lower frequencies. Yes, it may work to some extent, but remember, a wire is a 3-dimensional cylinder and all the eddy currents concentrate in the middle, having a much greater impact than my flat 2-dimensional copper. Okay, here's another idea. Skin effect literally increases the resistance of the wire. No, I'm not talking about the impedance due to inductance, but the actual resistance. Because the current, rather than flowing through the entire cross-section of the wire, flows through a thin skin. To measure the resistance, I typically run a bunch of current through the wire and measure the voltage across it, and that gives me the resistance. But in AC, wire also has inductance, so the voltage across it is a result of both resistance and inductance, which is a problem. Okay, I have an idea. I run an AC current through a rod as my wire, and I can check the current by measuring voltage across a 1 ohm resistor. Then I measure the voltage across the rod. Like this mess of a setup. Here's my rod with the probe wires across it measuring the voltage, which is the blue trace down there, which is just a few millivolts. And the yellow trace is the current through the rod that has a 1 amp peak. Now you'll see that if I have the probe wires wide and open like this, I read a higher voltage compared to if I bring the wires tightly close to the rod. Reason is, in the loop consisting of the rod and my probe setup, where current only flows through the rod and nothing through the probe wires, if magnetic fields generated by the rod mostly go through the loop, the voltage we read at the scope is the sum of the voltages across the inductance and resistance of the rod. But if we run the probe wires tightly close to the rod, then twist them back to the scope, making sure the magnetic fields mostly wrap around the probe wires too, we mostly only read the voltage across the resistance of the rod. Why? Because now the probe wire inductance and rod inductance are coupled together like a 1-to-1 transformer. The coupling is not 100%, but ideally, the same voltage that falls across the rod inductance is also coupled on the probe wire. And so we only read the resistor voltage. Beautiful plan! Here I tied the probe wires very closely to the rod. So here at 1 kHz I'm running a 1 amp peak current through the rod and I'm reading a voltage across it which is only like half a millivolts, which means the resistance of the rod is only half a milliohm. Now let's raise the frequency. The current remains around the same, maybe a bit less, but you see, as I'm raising the frequency, the voltage is getting bigger and bigger. So although the current is a bit lower, the peak voltage across the rod is almost double at around 35 kilohertz. So clearly the rod resistance has increased. Skin effect. I finally measured it. What's the use of the skin effect? Well, nothing really. It just makes for a worse resistance and wastes more power. You would think making a thicker wire would help, but really you're adding a ton of copper in the middle that current doesn't run through anyway. That's why in high power lines they can happily trade the wire core with a steel wire to make a much stronger wire that can hang over long distances without breaking. Or in induction heaters they actually use a copper pipe without affecting the coil resistance. But now they can run water through it to keep it cool. But I have to make an apology. In my early days of learning about skin effect, I thought that's what saves humans when they are exposed to high voltage, high frequency signals. I thought skin effect makes the current run only on the body surface, not hurting your organs.
Why doesn't it hurt?
Well, that's not the case. Skin effect is very dependent on the conductor resistance. You know, changing magnetic fields create an electromotive force or voltage inside the conductor that, divided by the conductor resistance, defines the amplitude of the eddy currents. So the higher the resistance, the lower the eddy currents and the less the skin effect. So inside the human body that has a resistivity of like 1,000,000 times more than copper, there is barely any eddy currents, and the actual high current can travel deep inside your body. The reason you don't get shocked and die is because your nerves don't react to frequencies over, say, 30 kilohertz anymore. So your muscles won't freeze. But the high frequency, high current cooks and burns you over time. So it's not an immediate death. You get to let go right away. What you can't let go of is my sponsor Brilliant after you get hooked on its quality educational material. Brilliant's interactive teaching method is easily the best way you can learn anything online. You don't just memorize, you absorb, you suck in the knowledge, you learn problem-solving skills. This semester, my daughter at school got a computer programming class on Python. And Brilliant very conveniently has a learning series on thinking in code and Python lessons. This is my chance to get her learn a ton more at Brilliant. All you need is to make a learning habit of like 10 to 20 minutes every day at your own convenience on a subject you like or need improving. For example, turn your bowel movement period into a light study session. I know you are on your phone, at least use it to learn. Do you want to get a lifetime 20% off Brilliant's annual premium subscription? Use my link brilliant.org/electroboom to sign up and start for free for the first month, and use the discount after you realize you are staying to learn. And learn by doing at Brilliant, with tons of interactive lessons in math, data analysis, programming, AI, science and physics and more. Become big brain now! And thank you for watching.